Okay, guys, chapter 6. In this chapter, we again covering the TNC system and TT, and starting to covering the IT system. The main important part of this chapter is IT system. Starting with TNCS grounding system, when we have protective multiple earthing or PME. The name is, I think, very clear. Protective multiple earthing in the system TNC system. Usually we don't have the earthing, local earthing, but here talking about if we have local earthing, what happened to the system. The protective multiple earthing PME system is a TNCS system employed as a grounding method for low voltage public supply and is used in several countries. So the name of countries are from Australia to US, UK is listed by here. The neutral conductor of the utility supply is solidly grounded at the source, which we're talking about neutral, of course, is solidly grounded at the source, and at the intervals along its distribution. So another extra grounding rods are connected along its distribution. At the residential unit service entrance, the neutral protective conductor PEN is connected to the customer protective conductor PE through the grounding bus. You can see by here the PEN and PE of this system and MEB multiple earthing bus. In this condition, the grounding fault currents rising at the user's installation will basically return to the supply through the distributor's neutral conductor, which therefore also act as a protective conductor and thus design a PEN system. In protective multiple earthing or PME systems, the main equipotential bounding conductor or MEBS of the building may be subjected to current even if the installation is switched off. How? This is contribution of the other faulty unit supplied by the same neutral network. As you can remember, in the class I discussed about a figure talking about upstream and downstream of the TN system, and we shows that in the downstream of the TN system the voltages is exactly in the same as the faulty voltage point, but it reduce as we going back to the means upstream, going back to the source. Unlike in TT system, the PME customer needed not install its own grounding system. However, the earth will be partially involved as a return pass to the source in the fault condition because of the connection of EXCP to the main grounding bus. You can see right here. Where it connect is essential to guarantee equipotential between simultaneous accessible metal part. Moreover, even in the absence of a ground fault, this earthing arrangement may cause the part of neutral current to return to the source through the earth. Therefore, in PME system, the ground become a path to the utility transformer and the circulation of the stray current is unavoidable. As you can see by here, even IG2 will conduct a current, means fault current a bit. In PME system, grounding fault current rising at the user's location have large magnitude as the return path is a conductor of both PE and PE PME. So during a fault, as the earthing resistance is a bit high, okay, and the other return path is PEN using PE as mentioned by here, if you can see PE. So therefore the total impedance of the fault loop, Z loop, may be low enough to allow the users to use the overcurrent device. So if the faulty current is very high, MCB or fuses can operate. To protect against indirect contact, a large ground fault current can easily fulfilled by this formula. We saw this formula before. IG, which is the fault current or ground current, is phase over Z loop, which in the TN system, as mentioned many times, the impedances of the PE or PN and the conductor, and if it's close to the source transformer, also should be considered. Hence, the presence of RCD in PME system is not mandatory safety requirement as in TN system. The combined neutral and protective conductor PEN may exist through the utility low voltage distribution system, as this allows some saving in the length of cable to be employed. Saving one cable from 4-wire distribution system, this is from the utility view, whereas within the user's installation, neutral and protective conductor may be separate, i.e. 5-wire distribution system. So as a users, you have 5-wire, but from the utility they have 4-wire. In some countries such as US and Norway, the use of PN conductor in downstream of the user's main distribution panel is banned. In PME system, the bounding connection is of almost importance at the service entrance of the developing unit between PN and PE. It is therefore essential to periodically inspect and maintain such a connection. So it's very important. Upon the losses of connection between PE and PN conductor, the building would become a TT system. So it's very good. In the case of disconnection of the PE or PN, the system convert our home or the unit convert to TT system, where in the absence of RCD, so if we convert to TT system, we need RCD to protect, which are not strictly necessary in TNCS. User exposed to electric shock hazard when fault happen. So from my viewpoint, if you want, mostly the system is used in the world is TNCS system. So otherwise, it is not suggested, it is not forced to use RCDs. Use the RCDs with the not small value, means not 30, around 300 milliamp should be good for protection against any fault and electrocution hazard. Then low voltage so for low fault loop impedance guarantee the safe operation of the user's overcurrent protective device with respect to the permissible times. In TNC system, the loop exclusively dependent on the parameter known to the user, such as impedance of circuits and transformer. In PME, instead of the fault loop impedance, includes the impedance of ZE, which is utility low voltage distribution system, which is usually unknown for the customer. So ZE increases with the distance of the fault location from the supply source, may change in time without informing the user because of modification in the utility distribution system. Of course, the distribution system every day change. Somebody install PV, somebody install the wind source, somebody means sometimes the utility install more loads, which are homes and other users. If the total fault loop impedance, which is the loop equal to ZE plus Z users, is too high, the ground fault current might be too low to the equation IG V phase over Z loop is not fulfilled, which this value, if this value cannot be fulfilled, then the overcurrent device would not be effectively protect the person against indirect contact. So that one should be too low. Otherwise, the protective device, which is MCB here, consider the case as the overload. The installation of RCD in the dwelling house can guarantee safety even in PME system when Z loop is too high, although the RCD is redundant in the case of low value of Z loop. So PME systems imply a considerable responsibility of the local utility, since together with the electric energy the distributor provides user with an earth connection and ensures public safety. In a fault condition, the utility PNE, although multiple grounded, may assume a voltage with respect to the earth touch neutral to ground voltage can be transferred as a shock potential to the user's ECP and EXCP. If utility cannot certify the neutral potential as harmless to the person in TN system, a TT system should be employed instead. So the utility check. If the TN system or TNCS system cannot be used, they have to change it to TT system for more safety. The PN conductor may become live due to a ground fault occurring along its distribution system. For example, as a result of the fall of overhead cable to the earth, you can see in the figure, I cannot see the cable falling on the earth. I can see the phase connected to the PNE somehow, or as a result of a contact of a line with EXCP, this one can be, not connected to the prospective conductor. So what's going on by here? There is a return pass RE to the from ground to the RN, which is the resistance of the distribution transformer neutral point. Rn represent the ground resistance of the utility earth conductor system. The neutral conductor is earth not only in interval along its run, but also at the customer's dwelling unit by means of their ground electrodes. RE is the minimum earth resistance of EXCP not connected to an equipotential system through which a fault may occur. The earth current by circulating through Rn and Re energizes the PN conductor, and thus the user's ECP again become energized. The contact resistance with earth also limits its ground current, and in some cases can be very high when we have sand or here mentioned snow, and I know if there is any dry soil or asphalt. The distributor overcurrent devices therefore may not be able to clear the fault within the maximum permissible time, exposing person to risk of electric shock. To identify the safe value of Pn potential and the maximum earth resistance Rn, let us examining this figure, which is I think very easy to understand the neutral value. So the Vn is the neutral voltage, which we expecting be zero always, but due to the neutral current we have neutral voltage. So V neutral equal to V phase times Rn, which Rn was the minimum of the EXCPs. The Rn is the resistance of the distribution transformer close to your house, close to the user's house, over Re minimum, Rn, Zi and Z phase. So Zi is the transformer resistance and Z phase is the phase resistance. These two values can be considered as a negligible value, and you can somehow delete them. So V phase Rn Re plus Rn again in this system as the TT. The voltage, the VST or VT should be less than 50 for the safety. Then from this point of view, we know the V phase, and we know somehow, of course, we know the Rn. Then easily you can calculate Re for the safety. From equation 1 we can derive the condition which must complete with to keep the Pn potential below 50. In some countries such as Germany, fulfilling equation 2 is compulsory requirement for the supply network operator. So as an example, PME system, there is a fault as a result of overhead cable fallen to a EXCP, such as a cold water pipe, where the EXCP has the equivalent earthing resistance Re 135 ohm and Zi phase ignored. Find Rn to keep Vn below the safe voltage, here mentioned 50. So Rn over Re should be less than 50, and the V phase also given. So if you calculate, you can find out that Rn should be 37.5 ohm. So at home, try this one. If Rn is 100 ohm, then what is the value for Vn?